All right, today we have gravitational potential energy. I put your assignment up on the board, even though we'll get onto Edmodo. It's just more reminding me that you have your assignment than and to put it on there than it is for you guys, because that's where you look. Okay, so our review, okay, that energy is stored within a system, okay, that can apply a force. Okay, so gravitational potential energy is energy that is stored within a system that can apply a force. Okay, there's a couple types. There's elastic, and there's electric. Okay, or in fact, there's many types of potential energy, elastic, electric. But the one we're spring, okay, etc. But the one we are going to talk about right now is gravitational potential energy. So we have a ramp. Okay, and my tastes have improved. I saw a car that I want, and so instead of a crate, I no longer want a crate for Christmas. I want a car, and the car looks like this. This is my car. It is awesome. I love my car. Okay, it's got the suicide doors. It's got the big old blower on the front. Okay, this is my car. Now, okay, we have a ramp. And the ramp goes up to a top. We've got a pedestal, and then down below, right down here, we have a cat. Okay, it is a sleeping cat. Because if it was awake, okay, it would be too fast. So, okay, so we exert a force. We have to exert a force on my car to push it up the ramp, up to the very top. Okay, and then we exert a teeny tiny force, just enough to get the car. Okay, now mind you, to get the car to the top of the ramp, someone had to do work. Okay, it's hard to push this big old heavy sedan up to the top of a ramp. Okay, it hurts my back if I push too hard. Okay, now, so the work that we did. Okay, we had to get it up there, right? Well, for intents and purposes here, we're going to take y. Okay, we're going to have to raise our car up a certain distance y to get to the top of the ramp. And so that means that we have our, if this is our positive y-axis, and that his height from here to the cat is a distance, we'll call it y initial. Okay, its height is y initial. We'll take 0 down here at cat level. Okay, so 0 is down here, and its initial height is y, okay, is this y initial. Okay, so how much work can gravity do? Okay, how much work can gravity do in this situation? Yeah, go ahead. No, just kidding. Okay. Well, work is based on the elementary is force times distance, right? Okay, so gravity has a force on the car. Gravity is exerting a force on the car here, this mg. Now, mind you, we nudge, this little slight force up here nudges the sedan over the edge. And then at this moment, we actually have a Looney Tunes moment. Have you guys ever seen the Looney Tunes rules of physics? I recommend that you go onto YouTube sometime and watch the Looney Tunes rules of physics. One of them is a suspended law of gravity. So the law of gravity only kicks into a sentient being once they realize that there is nothing beneath them. So we push a car out over the edge, and the car, okay, and if I'm in my car, I don't recognize that I'm about to fall until we fall, right? And until we recognize, oh gosh, I'm over the edge, and then you fall. Okay, so at that instant, gravity is the force acting on the car. Gravity will cause our car to travel a distance y the entire time the force is acting on the car. Okay, this work is equal to the gravitational potential energy. The amount of work that gravity can do on the car is equal to the gravitational potential energy. Okay. All right, and we call our potential U, and in this particular case, it's U due to gravity. UG. Right. U sub G, okay, UG. U sub G is our potential energy due to gravity. All right, so let's draw a ramp again. Here's our car climbing up to the top of the sedan, actually. Okay. I haven't named it yet. I will be coming up with a name. Okay, but it likes to be called a sedan, not just a car. Okay, so exert slight force to push it over the edge a little bit. Still has the gravity. We still have the y direction. We still have that. It's still gravitational potential energy. Let's get through with that. Okay, the work done is equal to the integral of f dr, because f dot dr, the integral of the force times the differential of its displacement. Okay, and in this particular case, it is mg negative j hat. We have taken positive y. We've taken up to be a positive y, so this force is acting in the negative j hat direction, yes? All right. Well, we're going to simplify this. Okay, this is going to be the integral of our force times our differential in the y direction, which is positive j hat. Okay, or we will take to be positive j hat. Okay, this integral is going to go from y initial to y final. So our work is going to equal mgy from y initial to y final. So that's going to equal negative mgy final minus mgy initial or we can flip those around, which would be mgy initial minus mgy final, and that would be our work. Okay, so our work is the force of gravity times negative delta y. Okay, but if our final is 0, then our u due to gravity up here is going to equal mgy, where that's our mass. G is our gravitational field. It's the acceleration of the gravitational field. Yes, we're introducing something a little new right now. I want you to write this as gravitational field. Close to the Earth, it is merely 9.8 meters per second squared. However, this is not going to change if we move further away. This value will change, but the idea that it is mass times the acceleration due to the gravitational field will not change. Times the position from our chosen origin, which in this case was the bottom of the cliff, which would be 0. Okay, is it possible then to have negative potential? Well, I sort of stole my own thunder there. Yes. And it depends on the origin that you select. Okay, so we could very well have selected this point up here to be our origin. Our y would have been negative, okay, and gravity would have done negative work. Or, let's draw another thing here. We're down there at the bottom of a well. Okay, go get Lassie. Okay, so this down here that's Corey. Okay, somebody threw Corey down a well. Okay, so we have to go call the fireman with no collarbone to jump into the well. So somehow we have to call Lassie and get Corey out of the well. Okay, if you guys even remember what Lassie is. Okay. Right. Yeah, so Lassie goes and barks at her owners. What's that? Corey fell down the well? Yeah, that's... All right, so if this is the case, then our gravitational work is going to be negative if we try to get him out. Okay, so if we do positive work coming out, the gravity is actually going to be negative work as he gets pulled out. Okay, that's the work that gravity would do. Oh, yeah, there. So the gravitational work needed to raise Corey out of the well would be negative UG. Got it? All right. So let's get back to our ramp here. Except this time, on the back side of the ramp, okay, we have another ramp. Much more gradual, and my sedan can roll out, and we decide to take mercy on the cat because I would never actually kill a cat. It's just fun to think about. Okay, as the car rolls away, okay, it doesn't matter that it's traveling in the x direction. And this is a pretty crucial point, that x is irrelevant. Okay, that x is irrelevant when we're dealing with potential energy. It only has to do with gravitational potential energy, only has to do with the object's height above the ground. Okay, and we can look at it like this, where we have delta r as our displacement up the ramp. Right here. We break this into delta x and delta y. The force is acting in the negative j hat direction. Our x displacement is orthogonal to it. And so what do we know about orthogonal? Okay, orthogonal vectors is that it's anything in the x direction when it comes to a force that's only in the y direction is irrelevant. It goes away with our dot product. So in this case, our potential energy, our gravitational potential energy, is path independent, and this is a very powerful concept here. Now, ironically, so is kinetic energy. Kinetic energy is also independent, and this is where this v squared is actually the dot product between the between our two velocities. Okay, it's velocity dot velocity. V squared equals velocity dot velocity, which equals v dot v cosine theta. However, if that cosine theta is 0, okay, then our cosine theta is then that whole thing is equal to just v squared. Okay, so so kinetic energy is also path independent. It's just how fast you're going. And that's it for gravitational potential.